Hi guys, my name is Dmitry and I welcome you on my technical channel. In today's workshop we are going to continue our experiments with FPGA using RTZ7 board developed and manufactured by a company called Digilint. In one of our recent workshops, workshop 4 to be exact, we designed an HDMI test pattern generator, and today we are going to use it as a baseline for a ZX Spectrum video controller. ZX Spectrum was a very popular home computer back in the 80s, and at the same time its hardware was simple. Yet its video controller had a special way of organizing screen memory layout, so that we can't get away with the standard IP core from Xilinx and would need to design our own VDMA controller. So let's get back to our project from the previous tutorial when we designed a test pattern generator. We're going to make a few changes to the Vivado project to begin with. Let's have a look at what we need to do on a high level. As you remember, we disconnected the output from AXI VDMA. The block itself is still in place because we want to minimize the amount of changes on the PS side. So instead, we connected AXI4 stream subset converter to our own piece of logic through external interface as access video. So it's not connected anymore to the output of AXI VDMA. Now, we will need to get access to DDRAM. In essence, we need to create our own video DMA block. So the easiest way would be to disconnect VDMA from AXI interconnect and make it external again. Let me show you the change on the architectural level. This is our old test pattern generator module, which I'm going to rename into ZX video. This is our old, previously designed process, which was responsible for frame generation. Inside that module, we also manipulated with color signals, RGB. This time it is going to be different. This time we're going to add two more processes, AMBA FSM process and color generator process. AMBA process will access DDRAM through AXI interconnect module using AXI interface. Then data will be temporarily stored in FIFO, which is 512 elements deep, and eventually it will be consumed by a color generator. This is the process that is going to manipulate with our color data based on the information received from DDRAM. So I'm going to disconnect VDMA from the AXI interconnect. Delete. Now I'm going to make external. Rename it into VDMA AXI memory to stream. AXI video clock. regenerate layout. Now I did a little bit of refactoring. I renamed this bus into VDMA axis memory to stream. It still goes into subset converter, which potentially we can get rid of, but we will do it a little bit later. Now going to the top level. On the top level, we added a bunch of signals which belong to the new bus. This is the one. And we also renamed test pattern generator into ZX video top. So again, we added the new interface to the top ZX video top level. Declared additional signals for the new interface. And simply instantiate a video controller. That's that. Instantiate ZX video top, and again we map the new port with the interface. Now go into the subfolder. Now it is called ZX video instead of test pattern generator. Inside there is an additional file, ZX video top, which in essence is just cross connection, if you like, between the top level and ZX video module, because in the future we're going to have more modules, so they all will be connected in this ZX video top, which just makes the design a little bit cleaner. At the moment, it's just a mapper between input interfaces coming from the top level and the ZX video instance of ZX video module. Nothing interesting yet. Let's go back to the changes that I have already made to the original process we used to have in test pattern generator. The MM2S FSM is pretty much unchanged. The logic is exactly the same, as you can see, with the only exception that we removed any manipulations with the color components. This is going to be done in P-color gen process. So the only small addition is that we will stay in VS idle state if the FIFO is empty. I will talk about it in a few moments. Going back to the Vivado project, looking at FIFO that we have already created. This is going to use native blocks, common clock built in FIFO. The clock is the same, obviously, for us. First word fall through. Right width is 64 bits and 512 elements deep. I don't think we can make it smaller. Yeah, exactly, this is the reason. Potentially we could get away with the smaller FIFO. And then that's about it. So we specified programmable full threshold, constant and empty threshold constant, which is a little bit smaller than the actual depth and a little bit higher than the empty state. So the values for the full threshold assert value and empty threshold assert value are not chosen randomly. The idea is that we need to have enough data in FIFO when we start a new scan line. So we have 256 pixels in horizontal resolution, so 256 pixels in a single scan line, which corresponds to 32 bytes. Here we have 64 bits, which is 8 bytes, and 32 divided by 8 means 4 elements. This is exactly how many we have. Let's have a look at the new elements of our logic. Let's first focus on the FIFO. We can find the exact set of signals from the IP itself. If we open stub VHDL, for instance, we can see the full definition of its signals. This is what we did, this is what we declared. This is generic, which we defined as 64 at the very top. 64, yeah. So now we instantiate a FIFO and then we map it to appropriate signals. Signals that we have already defined. Those are the actual signals related to FIFO. Now pay attention to the way how we enable writing into the FIFO. This is a combination of R valid coming from the interconnect, AXI interconnect, and also a condition that FIFO is not full yet. So we will be writing into it until it is full. Well, which should never happen, obviously, but it's just a good practice. Going to P-AMBA FSM process. It is relatively simple in terms of architecture. It has its initial state when reset is active, and it initializes signals to their default states. Now you can see that there is a pixel address which is initially assigned to this value. This is where it physically starts in our address space, the video memory itself. So as you can see, it translates into 8 and 6 zeros in hex representation. And then there is a typical state machine for implementation of AXI4 transactions. Sometimes it is called AMBA. The specification of it can be found in the internet. As you can see, it is called AXI4 specification. It can also be called AMBA AXI. So all the information can be obtained from this specification. Well, we implemented several states, which is idle, set address, wait for acknowledgement of the address, wait for data to start coming and start reading data. We count the number of chunks that we receive. In case if it's an error, we switch into error state, and then when it is done, we simply increment pixel address by the number of pixel data per scan line, because in one single AMBA transaction we receive enough data for one single scan line. Or if we already reach the end of the memory, of the Spectrum video memory, we simply wrap around and go from the beginning. Now a few moments to understand the logic of how the pixels are addressed. As you can see, a pixel address is incremented linearly, but the pixels in RAM are not stored in linear fashion. This is why we do those manipulations. To visualize this, it would be useful to have a look at the actual loading process of the screen. This is exactly what it is talking about. Attributes are placed linearly, the pixels themselves are not. So you can see they organized in 3 different areas. And this implies that we need to manipulate with the linear address. This is what we do in essence. Those are color attributes coming into play. A few things to pay attention to. There are quite a few parameters that specify the size of the AXE transaction. One is R size, which we can find in the specification. So it says 1, 2, 3 corresponds to 8 bytes in transfer. This is exactly what we have. And then the burst length, 4 transfers in a burst, and then burst type means incrementing. Please pay attention to those numbers as well. This is the resolution that we're going to work. This is the resolution for our HDMI display. And this is the native resolution of ZX Spectrum. As you can see, it is much smaller. So we're going to embed ZX Spectrum frame into our HDMI frame. So obviously, without scaling, ZX frame will look relatively small. Also, if you noticed, this is not widescreen resolution. It means that on one widescreen displays or monitors, it is going to be stretched across a horizontal direction. We are going to change this to a proper widescreen resolution as soon as we implement a scaling factor. Going to the next process, P-color gen. This is the process that reads our FIFO and generates data for our color components. As you can see, again, it initializes signals to their default state. And then it manipulates with color data depending on the state of vertical count, horizontal count, and the actual value that was read from the FIFO. So, first of all, on the top and bottom left and right areas, it generates a so-called border, the color of which at the moment is fixed to a specific value. But if it is in the active pixel area, then it keeps reading FIFO, and then depending on each bit in the red value, it either switches all three components to their maximum intensity or to the minimum intensity. This is going to generate a black and white picture with the maximum intensity that corresponds to bright white, and otherwise it is going to be just a black spot, black pixel. And this is all it does in essence. So in the end, our data stream is a combination of red component, green and blue. Now, if we switch back to the board design, then we can see that there is a stream subset converter. Which swaps the colors. So potentially we can get rid of this component by rearranging those three components, and then it will free up some resources. But let's not do this now. Let's try to synthesize the project and see what happens. I'm going to switch off my camera. Synthesis successfully finished, but before we run implementation, let's do one more step. I marked quite a few signals as debug, so we can use a technique called chip scope and observe how those signals change over time. So let's set up debug. I already added them before, so we already have all those signals. Will be created, found one clock, fine. And now we run implementation. Starting, I'm going to switch off my camera again. Implementation is done. Generate bitstream. Now, while it is being built, or rather rebuilt, let's have a look at what I did on the PS side. By default, it was configured to work in 1280 by 720 pixels, which I changed to our resolution for this experiment, 640 by 480. What I also did, it is the actual main, which only initializes the hardware and does nothing else. So how are we gonna test this? I'll tell you in a few moments. Build is finished. Now let's do a trick. Let's load a screenshot from the original ZX Spectrum into the area of video memory. I already downloaded one of the pictures. So this is a snapshot. So basically the data is kept in a format as it is kept on the original ZX Spectrum. So if we load it at the start of our video memory, then we should see the result, provided that our implementation is working properly. The only difference that we're not gonna see color attributes, so it's gonna be a black and white picture. So let's do this. Programming FPGA. And here we go. A small ZX Spectrum picture, black and white, yes. There is a border around it. No scaling, so the size is roughly the same. At least this is how I would expect it. The aspect ratio is not kept because we are not operating in widescreen mode. Well, this is what we're going to change in next workshop. Let's have a look at the last thing. Let's have a look at the chip scoping technique. We don't need it at this very moment. At least we are not desperate just because things are working fine. But this technique we are going to use in our next workshops. So let's have a look what we can get. So we can see available signals, which are from our chip scope definition. We can run it, and then yeah, we can see those signals change. Horizontal count, for example. Horizontal count is counting, as you can see. So this is very useful when it comes to T-ready, when it comes to debugging of our hardware. But we're going to spare it for the next time. Let's have a look at the original picture, which we are currently displaying on our hardware. So this is the original picture when the color attributes are working properly. In our case, we simply haven't implemented those attributes yet. This is why it looks like black and white, and then there are some artifacts but this is because of the absence of those attributes, color attributes. So guys, this is it for today. Please like this video if you liked it. Please hit the subscribe button. And next time we are going to implement scaling factor. We're going to switch to widescreen, and then we're going to implement color attributes as well. So stay tuned and see you later.